In the vast universe, there exist some of the brightest objects, the most powerful and dazzling quasars. What would happen if these cosmic giants collided? Quasars are among the most distant objects in the universe, the oldest and most radiant celestial bodies known. When the core of a galaxy gathers an immense amount of matter, including the remnants of stars, gas, and cosmic dust, this material can ultimately collapse, forming a supermassive black hole. Surrounding this black hole, a spinning accretion disk takes shape. The matter within spins at tremendous speeds, spiraling toward the central black hole. This is how a quasar is born. During this process, the matter heats up to extreme temperatures, releasing colossal amounts of energy. This energy causes the quasar to shine brilliantly, with light intense enough to rival an entire galaxy. Such is the nature of a quasar. If two quasars were to collide, the extreme interaction of matter and energy release could produce light far brighter than usual, blazing with unmatched intensity. Since quasars are already incredibly luminous, such a collision could become one of the brightest spectacles in the universe. This collision would unleash energy surpassing any known cosmic event, generating powerful gravitational waves. These ripples would propagate across the universe and beyond gravitational waves. The merger of two black holes would release intense electromagnetic radiation. This could transform entire galaxies, altering the surrounding matter and affecting the formation and destruction of stars. Once the merger of the two black holes is complete, their host galaxies would undergo profound changes. A completely new galaxy might form, characterized by an elliptical structure, the size of a quasar, or more precisely, the size of the accretion disk around the black hole is considerable. Yet, compared to an entire galaxy, the accretion disk is relatively small. Still, the light it emits and its radiant energy are astonishing. A quasar's brightness can match the combined light of hundreds of thousands of galaxies. For instance, our Sun has a radiative power of about 3.8 xyd watts. In contrast, an average quasar can emit up to 1038 watts, or even more. In other words, a quasar's radiative power is orders of magnitude greater than our Sun's by about 12 orders. An immense scale. Quasars are rare in the universe, especially in the modern cosmos. They were most prevalent in the universe's early stages, shortly after the Big Bang. But their extreme brightness allows us to observe them through powerful telescopes, even at vast distances. Scientists estimate that in the observable universe, there may be billions of quasars, though compared to the number of stars, they represent a tiny fraction. Despite their immense energy, quasars eventually fade as the surrounding matter is consumed by the black hole. The accretion disk runs out of fuel, and the quasar's brightness gradually dims. The quasar becomes inactive. Its central black hole grows quiet. No longer powered by a glowing accretion disk, it transforms into a typical supermassive black hole, interacting with its galaxy only through gravity. The central black hole may continue to consume nearby stars occasionally, or slowly accrete gas, but this growth is far slower than during its quasar phase. The quasar fades away, marking a rapid evolution in its host galaxy into a new phase. It's such a powerful quasar emerged in a nearby galaxy. Its high-energy radiation, including X-rays and ultraviolet light, could disrupt the stability of nearby stars and planetary systems, potentially destroying their structures. This intense radiation could heat and scatter surrounding matter, hindering star formation and reducing star birth in nearby galaxies. The strength and unpredictability of a supermassive black hole could pull in surrounding stars and gas, altering the dynamics of nearby galaxies. With advancements in observational technology, scientists use detectors like LIGO and Virgo to capture gravitational wave signals from black hole mergers. by analyzing the properties of these signals, such as frequency and amplitude. Scientists can infer details about the mass, spin, and energy released during the merger. In the near future, we will surely observe the life cycle of quasars with greater precision, perhaps even capturing their final glow before they fade away.